Hello, y'all. Hey, Dr. Mandis here. Hey, right now I want to talk to you about electronic transitions or why things glow in the dark. Alrighty. We've talked before in previous videos about the orbital diagrams of electrons, where electrons are within the atom, or most likely are within an atom. So here I'd like to say, hey, how do electrons move between the atoms? I said in a couple of videos ago before about the Bohr model, how Bohr talked about electrons moving between states, between energy levels, either moving up or moving down, and releasing set amounts of energy that came out of the work of Max Planck. So what I'd like to talk about is just transitions between states. What I have here on the left, right over here, the ground state. I just put one electron in the first energy level. If some amount of light energy comes in and energy is absorbed, it could be light, it could be sound, it could be heat, just some source of energy. If the electron gains energy, then he's not here on the graph, he's at another level. 2, 3, so let's just move him up to 3. If he comes all the way up to 3, that's what we call an excited state, has more energy. The process to go from ground to excited is excitation. Excited states don't last for long, just like in people. They don't last. The electron's going to fall back down to a lower energy state, any lower energy state, but we're just going to take them all the way back to ground. If the electron then falls all the way back to ground, then the energy that he absorbed gets emitted. It always gets emitted as a photon of light. Depending upon the energy of that photon, that'll describe a certain wavelength, and the wavelength gives it a color. So fireworks, next time you see them, you see all the pretty little colors. Just think of all those electrons moving from one excited state back down to a lower one and emitting certain wavelengths of light. All right. Let's look at just an aluminum atom. If you want to take an aluminum atom and just excite it, and that's what the little asterisk means, is that's an excited state, just pick one. Any electron will do. I have that little purple one there in the 2s. If we move that one up to, say, a high energy state, can't go in the 3s because it's full, but it could slap over into the 3p. So if it goes over to 3p, it will end up here in the 3p. What happens to the rest of the electrons? Well, they stay right where they are. 2 in the 1s. Now you only have 1 in the 2s, the 6 in the 2p, and the 2 in the 3s. If you notice, you now have like an incorrect diagram. That's how you can recognize an excited state. As far as the electron configuration goes, it's the same gig as always. Just write down the electrons that are in each level. You got 1s, 2s, 2p, the 3s, and the 3p. And so you write what's there. 2, only 1 in the 2s, 6 in the 2p, 2 in the 3s, and that, whoops, we missed 1 in the 3p. And those 2 electrons now in the 3p. The way you can recognize it on a test or something like that, if you're a student, is you look right there and you say, hey, that 2s isn't full and I got electrons up here. That must be an excited state. So what if, rather than exciting the electron, light energy comes in, the electron absorbs it. Instead of it moving to the first energy level, second, what if it moves so far up in energy that it's way out here and the nucleus can't feel it anymore. It can't attract it. The nucleus can't hold it in place. This electron didn't go up, went up so high, it's way up there. It's now free. All right. The atom has lost an electron, and so now it's becoming a cation. That's why it's called an ionization energy. The energy needed to remove the electron. It's not necessarily usually going to be this electron that gets removed. Odds are it's something way up here that's a little bit easier to knock out. All right. But that's what ionization energy is. And since it's an amount of energy that's going to be incident in there, basically we can take, again, that photon of light. And from there, from the energy, we could calculate a lot of good stuff. So let's just talk about light really fast. Light is a wave that kind of looks like that. It moves along multiple axes, but I can only draw 2 at a time. All right. And I just want to make sure that you know, hey, one point on one wave to a corresponding point on the other wave is called a wavelength. And the wavelength is lambda. It's in nanometers because it's a really small amount. It doesn't have to be crest to crest or trough to trough. Just one point on the wave to the corresponding point on the next wave. Frequency, it's kind of like this. Say you are the bystander. You're standing there watching the wave go by you. How often does each wavelength pass by? That's per second. How many wavelengths per second pass you by? All right. That's why frequency is just literally how fast it's going. It's the frequency of it. Wavelength is in nanometers. Frequency is per second because it's a number per second. Cool? All right. Since we have per second and nanometers, what we have is distance divided by time. We call that speed. The speed of light in a vacuum is a constant. That is 2.998 times 10 to the 8th meters per second. Speed of light will vary depending upon the medium, but we're just going to use the speed of light in the vacuum as our constant. The energy of the light depends upon two things. It depends upon the wavelength and the frequency, and they kind of go together. Longer wavelength, shorter frequency, because it's going to take longer for the wave to pass by. Shorter wavelength, greater frequency, they go opposite. But how fast that light's moving, so to speak, that's going to be reflected in its energy. So energy is going to be inversely proportional to wavelength and directly proportional to the frequency. So if E equals hc over lambda or E equals h nu. Okay? The h is Planck's constant, another number that you would just memorize, 6.629 times 10 to the negative 34th joules per second. Okay, so basically we can calculate the energy of a photon based upon its wavelength or its frequency. That's going to be really useful because we can take that back up here where we were exciting, where was that? We were exciting the electron out. Since we know the energy, we can relate that to the wavelength, we can relate that to the frequency nu, and we can do a lot of good stuff with it. All right, so let's just play around with the frequency real fast. What's the wavelength of a photon given its frequency? All right, you would want to say, C equals lambda nu. That's a constant. You can have the frequency, you can solve for the wavelength. Once you have that, you could either get the energy from the wavelength or the frequency. I have that on this slide. C equals lambda nu is a great way to relate lambda and the length and frequency. It's one you should know. And if you have one of either of them, you could always calculate the energy of the photon. It's just plug and chug. They look intimidating because they got joules, seconds, but the seconds would cancel, just leave you with joules. Don't get too nervous about the scientific notation. So it's scientific notation. Big whoop, you're going to use a calculator to calculate it anyway, I would imagine. So you just plug in and go. More interesting questions. If you have a sample of boron atoms that's emitting so much energy of light, so much energy when a sample of light hits it. Basically, that incident of light, you got a pile of boron, light comes in at 250 nanometers and so much energy, okay? How many atoms of boron are in the sample? The thing that you really want to wrap your head around is that this is about a photon. A photon of light has that wavelength, and a photon strikes a atom. I know it's an atom, but stick with one, all right? So we would like to get from joules to atoms, okay? We're going to use the ratio of joules per atom. How do we get this ratio of joules per atom out of the nanometers? Because if we convert that nanometers to energy, then that would be the energy per photon, which would be the energy per atom. And then we could plug that number right into our conversion factor and convert joules to atoms. So we do the E equals hc over lambda, plug in your h, plug in your c, plug in your wavelength in nanometers. Okay, if you notice, my scientific notation isn't great there. That's not nanometers, that's meters. Sorry about that. Nanometers, nano means times 10 to the negative ninth. So all you really want to do to convert it to meters is 250 times 10 to the negative ninth meters. It's not pretty scientific notation, but it works. Okay, then you can get your energy. Plug that is so many joules. That's what I was saying. The energy is joules per photon. Okay, it's like if you go to buy something, it's $200. So it's $200 per item. Okay, well, so many joules per photon and one photon per atom. So we can plug that number back up in there and do the conversion. And the next one, you have this photoelectric effect. This first started with Einstein. Okay, if you have metal with an incident amount of light on it, it could remove the electron. That's what we've been discussing, is this photoelectric effect. Okay, how much energy is required to remove one electron? Well, we know the energy per mole of electrons. We could probably do the conversion factor there. And then once we have the energy, we could get the wavelength of that. Okay, so we know the ratio kilojoules per mole, 318.2 kilojoules per mole. Somehow we want to use that to get energy. So I'm sort of saying, hey, that's where I would start. All right. We want it per electron. So you think, hey, I want to convert this around. Okay. So each electron, if it's 318 kilojoules per 1 mole of electron, then how many per electron? So I could probably use some Avogadro's number gig there. All right. And then I can cancel out moles. Use Avogadro's number here, number of electrons per mole, cancel electrons, get to kilojoules. It all, you got to see that that's your conversion factor. So we would need moles of electrons here, and we'd be good to go. That gets us to the energy. We now to say, hey, energy is hc times lambda, and then we could get the wavelength from the energy. Cool? I know I hustled through some of that math, but just pay attention. Remember that it's joules per photon, joules per atom, and use conversion factors, and things aren't so scary. Just focus on units, not numbers. Up here, we focused on the units, which could let us to the units, and then we just happen to plug in Avogadro's number. If you focus on letters first, life's a lot easier. Well, I hope this helps with your photoelectric effect. I'm sure you're going to love it. It's good times. Take it easy. I'll talk to you later.